Moore's law might be dead. For decades, we've relied on the idea that the number of transistors on a microchip doubles every 2 years, leading to exponential growth in computing power. This principle has fueled the digital revolution, enabling everything from smartphones to the internet. But we're reaching the limits of silicon-based electronics. Transistors are now approaching the size of individual atoms, and we can't go any smaller without running into quantum and thermodynamic uncertainty.
This means that you can't shrink them anymore. The world has decided that path towards making computers better is making them bigger.
And all the while, our ambitions for artificial intelligence are skyrocketing.
The last 7 years has been an incredible time for AI. The compute has gotten so fast that in many ways the networking is now the bottleneck.
AGI isn't just a concept in sci-fi anymore. It's a tangible goal. But achieving AGI will require vast amounts of computational power and data, potentially far beyond what our current technology can handle. So is that it? Is it the end of computation in Moore's law? Or maybe the next step is beyond the atom and towards the speed of light. Using light, some believe the answer lies in photonics, a popular subject in computational literature, but never before has it seen mainstream commercial usage. Until now.
We've built photonics at a scale that no one's ever seen before, something that just wasn't possible over the past decades.
And at the forefront of this revolution is a company called Lightmatter. Light has been revolutionizing how we send information since the 1800s, when people started sending signals using flashing lights and mirrors. But the real breakthrough came in the 1960s with the invention of fiber optic cable. Thin strands of glass that can trap light and use it to send data. This transformed how we communicate today. Most of the internet now runs on these vast network of undersea cables connecting us to the internet. While as a species, we've gotten really good at sending information using light, actually computing with it, or using light to do math, has been much harder. But scientists have dreamed about optical computers since the 1980s, because light is so much more fast and efficient than electricity. But controlling light for computation is incredibly tricky. Light wants to spread out and scatter, and getting it to make sharp turns or stay in tiny spaces goes against its very nature. It's taken until now for science and companies like Lightmatter to start making technology like photonics viable. Photonics is the science and technology of detecting, generating, and controlling photons, or light. By contrast, photonics uses optical fibers, or waveguides, on a chip. This means data can be transmitted faster over longer distances and with less energy lost. And Lightmatter is pioneering this field by integrating photonic components directly into computer chips, enabling the new method of chip communication that could lead to AGI. To understand better how this technology works and the limitations of today's computational methods, we filmed with CEO and co-founder of Lightmatter, Nick Harris, in Lightmatter's Palo Alto lab.
We're in Palo Alto, and we are working on what will be the future of how computer chips and the supercomputers that power artificial intelligence are going to be built. I'm Nick Harris, and I'm the co-founder CEO of Lightmatter. At Lightmatter, what we're doing is we are enabling these AGI supercomputers that are being built towards realizing these machines that are able to think at the same caliber as the best humans on the planet.
So what is AGI? AGI, or artificial general intelligence, is a bit of a hot topic lately. And the general theory is that it's an AI that could be capable of understanding, learning, and performing any intellectual task at a human level, or maybe even better. However, recent acceleration and the AI boom we're living through has made us take it a lot more seriously. What would it take to make it real, and what would it take to compute it? Named after IBM researcher Robert Dennard, for decades this was the magic rule of computing. As we make transistors smaller, they would use less power and run faster. It's why your phone today is more powerful than a room-sized computer from the 1970s. But around 2006, this free lunch of better performance ended. We hit fundamental limits of physics, and suddenly, making chips better got a lot harder and a lot more expensive. This is why companies like Lightmatter are so exciting. They're trying to reinvent computing itself to keep scaling as we've known it going.
So my name is Simona Jankowski. I'm the new CFO here at Lightmatter. I was previously at NVIDIA for 7 years, heading up investor relations and strategic finance. Amazing time to be there. Lightmatter is a pretty amazing company. It was tough to leave NVIDIA, I have to say. It took a lot of sleepless nights and a lot of deliberation and thinking about it. It came down to, in terms of my decision to come here, is the combination of the team and the technology.
How did you first get interested in computers?
So I think for me, interest in computing maybe started with gaming, and then it was figuring out how to write game programs and how to create websites, and then how to build computers. And then once you're building the computer, the question is, how do these things work and what exactly is going on inside the machine? I went to work at a big semiconductor company studying transistors, which are the device that ultimately powers all modern computers. And what I learned there is that there were some fundamental challenges associated with continuing to make computers better, faster, more efficient. What I discovered while I was figuring out how I could contribute to computing in general was that light was probably going to be a very big part of the story. And so I went to graduate school at MIT and studied photonics using silicon, the same platform that all computer chips are built on today. And I specifically studied quantum information theory and quantum computing. What I learned along the way was intricately how light works and what the future might look like with light.
Compared to electrons, light is pretty ideal for communication and transmission of information. It enables faster and more reliable interconnects over long distances because it's literally traveling the speed of light. Also, light generates less heat and consumes less energy, making it sustainable for large-scale systems like these AI supercomputers we're talking about today. While electrons dominate the field of computing today, companies like Lightmatter, well, are trying to make light matter.
When people think about light, they think about the colors. They think about light emitted by the sun. But it turns out that everything that has a temperature is shining light. And light is actually fundamental in how we build electronics today, but people don't quite realize it. It turns out that the signals that radios send and many forms of communication are actually already light. And the problem is that people haven't quite realized that light's going to be going into computer chips to make them faster and more efficient. And we're working on that future.
Lightmatter was the first ever company founded to commercialize photonics technology, and now they're ready to talk more about their two products, Passage and Advise.
So this is Passage. This was built in 2019. It's a 200 millimeter by 200 millimeter chip. So what's included here is an array of 48 maximum size chips that are stitched together with optical waveguides going across the entire platform. And by bringing waveguides close to each other and building different geometric shapes, we're able to manipulate light, encode information in light, and ultimately enable these GPUs and switches to build these data center scale supercomputers. There are optical fibers. The same glass technology that's used for connecting the world is attached to the side of our photonic chip built on silicon. Ultimately, Passage looks a lot like an electronic chip, except that we've got light moving around the die. And if you look at it through an near-infrared camera, you'll actually be able to see what's going inside the chip. And what we're able to do is, by programming the chip, we can set up how all 48 of the tiles sitting on top of Passage are connected. And the way that this works is you take a customer GPU or a switch or a CPU, and you integrate it on top of Passage, and now those chips can communicate using light. So we realized that there were some fundamental challenges both with how chips do computation and how they transmit information between each other, especially in the context of these large AI workloads that use teraflops and petaflops of computation, operations per second. And what we realized was that by using silicon photonics and using light, we would actually be able to drive the energy efficiency, drive the speed, and continue the roadmap for computing. And here is what's coming soon. So this is the next generation Passage, and it's able to communicate at over 100 terabits per second. So in this chip, we're able to attach 256 fibers, the largest optical fiber count in the world, and the highest bandwidth chip in the world.
Think of this as a superhighway for data passing between different chips. It uses light to transmit information between processors, enabling unprecedented bandwidth and ultra-low latency communication. This opens up a new frontier of speed and interconnectability that current GPU clusters lack today. Additionally, as we try to push more data through more interconnects around the chip, we run into what's called the shoreline problem, where you're literally running out of space to plug electrical wires into the chip. Photonics sidesteps this entire issue by using optical waveguides within the chip itself. This allows for data to be transmitted through the entire chip, massively increasing the potential bandwidth.
This is actually the flow for assembling one of these Envise chips. So you've got two 25 billion transistor die, and those die get attached to the substrate, and then you flip that over. You attach the 4 photonic cores, and then you attach another substrate that allows you to communicate with the socket electrically to deliver power and signals. And that turns into this chip here, which goes on the card.
In electronic chips, data transfer is limited by the electrical resistance of the materials and the capacitance of the circuits, which causes delays and energy loss. Envise is its own all-in-one photonic computing chip. It combines traditional electronics with photonics to perform computations using light. This isn't just a small upgrade, it's a completely different way of thinking about computation. Imagine data flowing through the computer at literally the speed of light, using different colors to process multiple things at once. While traditional computers are stuck waiting for electrical signals to bounce back and forth, like a very fast ping pong game, light moves through these chips without any delay. And here's what's really clever. They can stack what Lightmatter calls virtual processors on top of one another, almost like creating multiple computers in the same physical space. They're doing all this while using far less power than regular chips, which is amazing because energy is one of the biggest costs in computing today, especially for AI. This isn't just making computers a little better, it's reimagining how they work with light. As overall computing performance is increasing, today's bottleneck is not about the chips or the speed of these chips. It's about the networking or the interconnects between these chips. That's the bottleneck we're seeing today. Networking is the communication and data exchange between multiple processors or chips or integrated circuits within a computing system. Networking is critical for enabling efficient performance in modern multi-chip systems.
The last 7 years has been an incredible time for AI, and a lot of what I saw is the unbelievable increase in the pace of computing, 1,000 times increase in the performance of a single chip, which was amazing. Even more amazing in that it came after Moore's Law had essentially ended. But a lot of those advances are starting to hit certain walls. And most of that has to do with the connectivity. So the ability to connect thousands, hundreds of thousands, and millions of those chips to each other to be able to communicate at the speed of light. And that's really what's going to be needed for the next 10, 20 plus years in computing. And so the next challenge was really the one of how do you interconnect them at scale?
Transistors are so small at this point that they're approaching the size of the electron. And this means that you can't shrink them anymore. So you've got to figure out a new way for chips to get better. And the world has decided that the first path towards making computers better is making them bigger. The reason it's troubling that transistors were hitting bottlenecks and fundamental limits is that in almost every field, these things are all tied to progress in computing, our ability to simulate the world, perform calculations, connect in real time. So if progress wasn't going to continue at the same rate it always had been, there would be a slowdown in the future coming. And I wanted to make sure that that wouldn't happen and try to figure out how you could augment computers, sort of like the Bionic Man, and add light to these systems.
My name's Steve Klinger, so I'm VP of Product with Lightmatter. I've been at the company for about 2.5 years.
Tell me more about how the chips themselves and their speed isn't necessarily the bottleneck, but that it's more the networking between them.
There's, I guess, a few relevant trends here. One is pretty well known that the size and complexity of the models over the last few years has increased dramatically in these large language models. To train something of that scale, you need a huge number of compute units. But the challenge is they actually all need to be able to communicate at very high speed with very low latency or delay amongst one another. In the traditional design, those compute units, the points at which they're trying to escape all of this data, they're bound by the shoreline of the chip. So the electrical shoreline of the chip is the fundamental limiter. You just run out of space to put the high-speed signals that are sending all this data. And the only thing we could try to do is make those signals run faster. At a certain point, you just can't fit more of them. What we're doing is we're allowing bandwidth to escape anywhere in the area of the chip. You get a dramatic scaling in the amount of bandwidth that can be simultaneously communicated outside of these chips. Also, they can simultaneously communicate with more similar chips.
Today, the biggest supercomputers in the world are around 100,000 GPUs, and that's doubling every year. The challenge with today's supercomputers is that the life of a GPU in these systems is one where they're sitting there waiting for data from memory, twiddling their thumbs, waiting for data from the neighboring GPU, And one of the really big challenges for the computer scientists and machine learning scientists who train AI models on these supercomputers is figuring out how to leverage the fact that it's not really a single supercomputer. It's a bunch of little supercomputers that are tied together with very low bandwidth interconnect. And at Lightmatter, what we're doing is we're enabling these supercomputers to act as a single massive chip. So today, if you look at how GPUs are built, they sit on top of a silicon substrate. And you've got a GPU and the memory elements integrated on top of that silicon substrate. What we're doing is replacing that silicon substrate with a new silicon substrate that enables those chips to send data using light. And so what we've managed to do is figure out a way to slipstream next generation technology into the existing ecosystem.
To see this innovation up close, Lightmatter has built their own mini fabrication facilities and uses advanced microscopy to develop and inspect their chips. Having these capabilities in-house allow them to rapidly prototype and iterate on their designs. Ritesh Jain, Senior VP at Lightmatter, gives us a tour of their cleanroom facility.
I am a Senior Vice President here at Lightmatter. I lead the engineering and operations team. My team essentially focused on building products that are end-to-end, all the way from silicon engineering down to system level and rack level validation. So this is our clean room facility. This is an end-to-end capability where we're going from a silicon that's showing up on a wafer all the way out to a packaged unit that has fibers attached that can be deployed into a system for verification and validation at the system level. What you're looking at here is essentially our, the fiber attach process, where we're dropping the FAU onto the V-groove bank, and we're using that shining light. We're evaluating whether or not there's active alignment of those fibers in the V-grooves. And then once that's done, once the active alignment is achieved, we're able to dispense epoxy to ensure that we can seal the fibers in the V-grooves.
Here we're looking at the waveguides that lead to the input of the chip. So this is how you get light into Lightmatter's products. So here you can see the waveguides. The optical fibers sit in these grooves. They're actually like a V that's etched into the silicon. So inside of each one of these fibers, we have 16 colors of light. And these are all around a wavelength of 1300 nanometers in wavelength. And the light is coupled into the waveguide that's built into the silicon. The waveguide is a few hundred nanometers wide and about 100 nanometers tall. And inside that tiny little device, you've got 16 colors of light that are traveling together. The reason light was interesting is that it relies on a fundamentally different set of physics. Computers today are built on electronics, and in electronics you have this particle, the electron, and it's governed by a specific set of properties. There are things like resistance, inductance, and capacitance, and these describe the power dissipation, so how much energy the chips are using, how fast the chip itself can switch. And you compare electrons to light, what you start to realize is that light would be very interesting. It doesn't have a concept of resistance or inductance or capacitance. Light is operating in the hundreds of terahertz regime. Electronics are operating in the gigahertz regime. Some other interesting properties are parallel communication that's able to happen in a way that you can't achieve with electrical signals. Silicon photonics has been developed over the past 20 years. Around the year 2000, the technology really started to reach some level of maturity where they started to think about what systems of photonic components might look like. Now, the challenge 20 years ago was that there were no foundries or commercial partners that would be able to take these things and scale them. And there was a bigger problem. Electronics and electrical wires were still the main medium for doing this, and those wires were able to continue making progress at a sufficient rate for people to not look at what the future might look like. And at Lightmatter, what we've done is we've built photonics at a scale that no one's ever seen before. Millions of optical components on a chip, something that just wasn't possible over the past decades. I love chips. Every time I get to see one of the chips that we're building, it blows my mind. From the work that I did in graduate school with my co-founder, Darius, to today, the advancements we've made are huge, and it's just pure joy seeing the things that we built.
Developing this kind of technology isn't easy. In fact, it's never been done before. It requires significant investment, cutting-edge research, and the perseverance to overcome technical challenges. But the potential rewards are immense. The death of Moore's law doesn't mark the end of technological or economic progress. Instead, it marks the beginning of a new age of computing, only limited by the speed of light.